Okay, good afternoon, everyone. Welcome to this invited talk by Professor George Karabatis. George is visiting us from the University of Maryland in Baltimore County in the US, and he's here with us during the current semester on a sabbatical leave. A few words about George. He's both a professor and an entrepreneur. He works, as I mentioned already, at UMBC in the Department of Information Sciences. He is also the Director of Entrepreneurship and Innovation minor at UMBC. And he has degrees in computer science, PhD and master's, as well as a mathematics bachelor degree. And before joining UMBC, he was a research scientist at Telecordia Technologies, the former Bellcore. His research interests are in various aspects of data science, specifically on identifying and extracting information using semantics and context in an intelligent way to solve interesting problems in research areas such as information and systems integration, detection of cyber attacks, including 0 days, data anonymization, etc. His work has been published in journals, conference proceedings, and book chapters, and he has co-edited a book on information fusion for cybersecurity analysis, which was published by Springer. As an entrepreneur, he co-founded 3 startup companies with the help of his students. It is a real pleasure to welcome George here at the Technical University of Crete. It reminds me of the first time we met, which goes back 23 years. In year 2000, as a PhD student, I spent the summer in the area of New Jersey at AT&T Labs. And that's where we met first time. At the time, you were working at Telecordia, Bellcore. And 23 years later, I couldn't imagine that I would be in the position to welcome you at the Technical University of Crete, but we're glad you're here. And the floor is yours. The title of the talk is The Role of Semantics in Systems Integration and Cybersecurity. So once again, thank you for coming to the Technical University of Crete and for delivering this talk for us. Thank you.
Thank you so much. It's a pleasure to be here among all of you and to share my thoughts on a few research topics that I hope will be of interest to everybody. Συγγνώμη, αλλά να ζητήσω συγγνώμη από τώρα, γιατί η ομιλία θα γίνει στα αγγλικά, γιατί ήμουνα στην Αμερική για 39 χρόνια και η ορολογία που θα χρησιμοποιήσω δεν υπήρχε στα ελληνικά τότε. Οπότε μου είναι κάπως δύσκολο να τα πω στα ελληνικά, οπότε θα γίνουν όλα στα αγγλικά. Okay, so let me share my screen and we get started. Okay. So the title of the talk is The Role of Semantics. And today I will be talking more about semantics than anything else and how this mostly affects 2 areas of research. One is systems integration and the other is cybersecurity. So okay. So the outline of the talk is the following. A little bit about semantics at the beginning so that to get everybody into more or less the same footing. And then we're going to start getting into other areas like systems and information integration using semantics, cybersecurity using semantics, anonymization using semantics, and GIS. At the end, I'm going to go a little bit about possible collaborations that may happen since I am here as on a sabbatical as a visitor, and I will be around for quite some time. So a few things about me. As Professor Labudakis already mentioned, so I'll go briefly. I do not like to talk about me. So I was in Bell Communications Research. It became Telcordia. It changed through several owners. And I think still now it is under Ericsson, the mobile operator. And I've been working on applied research problems in the telecommunications industry. And later on, I went to the University of Maryland at Baltimore County, UMBC, and I've been there since 2002. And now I am here in front of you. So I really appreciate this opportunity to give you this invited talk about important aspects, I hope, to you. As I said, the whole discussion today is going to evolve around semantics. And the research topics that I like to touch using semantics are the small circles around the big one in the middle. So starting with cybersecurity, there is intrusion detection, like how to identify cyber attacks, software vulnerabilities, how to identify flaws in software code using semantics, application integration, how to put together different entities, systems, software systems, special query enrichment, how to get relevant information when you are asking for GIS queries, and anonymization on how to utilize techniques to anonymize data sets so that they can be publicly available without allowing others to get back into the original data set. So let's start with semantics and systems integration. I would like to first pose the problem that we try to solve. What is the whole thing about? And it has to do with companies that buy one another, or companies that have a lot of branches and they want to consolidate, or what we call mergers, acquisitions, things like that, which is something that we all see every day. Okay, at least in the US, and I guess here also, we have seen one bank buying another. We have seen airlines buying each other. We have seen consolidation of factories, of industries, of a lot of things. So what is happening when the point comes that the legalities are over and now we have to actually do the work? So in general, there are two IT departments after the consolidation. What to do with those two? You have systems in one company, systems, software systems in the other company. What are you going to do with those things? Are you going to get rid of one? That will be the most plausible idea. But then what are you going to do with the customers that were inside the system there? You're going to lose half of your customers? It doesn't make sense. So we have to do something smarter. We have to consolidate. How? We have to get rid of one. We have to, what are the different things that we can do? Here comes systems integration. So markets require companies to respond when things like that change. How the companies are going to respond? Either they're going to become flexible and change things, or they will go bankrupt. There's no other way. The fittest survives. And this is what is happening there. So in order for them to survive, they go and create integration projects. What are the integration projects? Projects that are trying to put things together, either two software systems together, or leave them as is, but have something on top that allows a third party to go and ask information that comes from all the underlying systems. And this is the most plausible approach. So integration is a necessity, and it is happening. But if we look at the integration projects that happen, they are very much time consuming. They take years and years and years. They're expensive. They are not only that, but they have something that nobody likes to talk about. a very high failure rate. The success is dismal. So with a rate of 84% of failure, we are in trouble. And although they pour a lot of money into integration projects, larger integration projects have higher failure rate than smaller ones. Why? Because smaller ones cut corners. Smaller ones have a few goals. Smaller ones are easier to manage, and smaller ones can be done within a shorter time frame. So it is not a simple problem. It is something that comes to us with a lot of issues that we have to solve. And most of all, 50% of the IT budget in a company goes to integration problems, solving integration. So we're talking about having a lot of resources and doing nothing. So what's going on? Something is an issue here. So what is it? The bottom line is that it is the semantic is missing from what we try to do when we try to put things together. So what's semantics? It is the meaning of things, the meaning of words, the meaning of what we have in front of us. When we create a software system, the programmer gets the specs and start implementing. And then the programmer implements things by interpreting things in a certain way. Later on, let's say a decade later, when the software system is going to be integrated with another one, how would we know what that programmer had in mind when they created that system? We don't. We interpret our own way, and here we have a mismatch, and things do not work. So, for example, we want to be able to identify what we really mean when we say a word. And you can always try this yourselves. If we try a word on Google, like the word credit, we get 7.3 billion links, okay? In very short amount of time. One would say success, yes, great. Now, is it success? Yeah. Are we going to go through 7.34 billion web pages to see what you're looking for? Absolutely not. What's the problem? It is too generic. We just gave a word that has multiple meanings. Google tried to give us everything possible. And when we have so many things, we cannot really get exactly what we need. So we need to add more semantics to what we mean. So we have to try to give more meaning, more semantics. So if we start adding more keywords, things are going to start changing. So what do we mean? Provide more context, which is more semantics. If we put credit and then university, we get from 7.3 billion to 1.4 million. Way, way better. But still, it is 1.4 million links. We still cannot go through all of them. But if you add more context, like a specific course in a university that has so many credits, then you're going to find basically what you need. We are like 116 links. So what I want to say is that by giving emphasis or putting more information that has to do with the meaning of what we are looking for, we prepare the one who is looking for things to get better answers. And we want to do that in other areas. So coming now from the, yes, sure.
Okay, so I buy the premise that when we search for something on Google or any search engine, that it's okay. Sometimes we ourselves try to narrow it down by guessing extra semantics and extra information. At the same time, there is the recommender of the platform, right? Of Google. So it tries, for example, you will never search the 1 billion indeed searches, but the recommender is trying to narrow down and give you the top 10 supposedly the ones that it guesses that are more relevant. So how does the recommender, so is it that the recommender fails and the top 10 are just as useless as the bottom, I don't know, 1 million?
Yeah, actually that's the recommenders trying to use semantics to come up with the answers. But personally, I do not like to put cookies. I do not like to know that Google to know what my history is. So it does not have much information about me. And it is like when you start from scratch, you give an ambiguous word, you're going to get tons of hits. But you're absolutely right. Recommender systems use semantics behind in order to come up with more and better qualified answers. But they need these semantics in order to do it. They cannot do it just like that. They cannot guess what it is in our minds, which is more or less similar to what we use when we have, let's say, we read a sentence, we read a paragraph, and a word in this paragraph may be ambiguous, but we can decipher exactly what that word is by looking at the context surrounding. So if you know in the paragraph that you're talking about, let's say, a university environment, you know that these are your boundaries. Every word that it is ambiguous may be deciphered by being qualified with a university environment. So we as human can do that, and this is great. But we want to go beyond that. We want to make the machine have some capability like that. So a machine can comprehend the purpose of the data. Think of whatever we are giving to the machine by recognizing the actual meaning of the data in a computing environment. How? We want to do that. We want to make the machine be, I cannot say smarter because machines are dumb. We want to be able, the machine to hone in better into what we mean. And this is where semantics comes. Current approaches that try to put systems together, they do it using ad hoc adapters. Basically, I have one system here, one system there. I'm trying to find correspondences between those two, and then I'm going to write a small program that takes input from here and sends it there. How do I do that? I look here, I look there, I'm a programmer, I can do that, and vice versa. However, this is not a scalable solution. Number one, it's very expensive. You have to pay programmers all the time to do it. Number two, if you have thousands of those objects around, you need to have n-1 adapters every time you have a new thing. So we're talking about an intractable problem. It is very difficult. It is time consuming and it's expensive. So why it is happening? Because the fundamental issue is we cannot use an automated mapper from one object to the other. So I'm going to talk a little bit of how to create a mapper like that automatically finds one object here and tries to identify what is the corresponding object there. How do they do that? Just like we have an intuition and we can tell, we try to put some of that into the computing environment. So let me give you an example of within, let's say, the database environment, where we have two tables. One table belongs to application 1 in system 1, and the other table belongs to application 2 in system 2. And suppose we want to get information from both. So look at those two tables, clients and customers. And human can tell, oh yeah, this is very much similar. Clients in one system are called customers in the other one. So if we merge those two companies, we have those two tables, we have access to those two tables. And the CEO of the company, of the new company, will say, okay, I want you to give me a list of all the customers that I have in both systems. As a database problem, this is very simple to solve. What do? Select name from clients, select CNAME from customers, you get the two result sets, and then you put them together using a union. But if we try to do it automatically, we have a problem. Name is not equal to CNAME. Clients is not the same. Clients is not the same as customers. So automatically, if we try to have a system that does this, that system cannot do anything like that from scratch. It needs some help. It needs some help from us. What do we need to do? We need to, let's say, create a system on top that system has all the correspondences between the top and every one of the local participants. And when we get a query on the top system, which, by the way, let's call it that it is customer, get me, let's say, customer name from customer, that query will be split into two subqueries. One will go to system 1 and will become select name from clients. Another one will go to system 2 and will become select CNAME from customers. And then will automatically execute independently in both systems. We'll collect the results and then put them together using a union and send them back to the original user. So this whole process is a simple example of using semantics. What are the semantics? Somebody must say that clients and customers are the same. Some must say that name and CNAME is more or less the same or correspond to each other. So we need to have a mapper to map things on top with things on the bottom. If we do that, we have the capability to get more things done. So the same thing now is, let's say, in the system perspective, we have, let's say, 3 systems. What we need to create a layer of abstraction on the top, and that layer of abstraction will contain information about mappings from the top layer to system 1, top layer to system 2, top layer to system 3. And users can send queries to top layer, and the top layer will take advantage of whatever semantic information we have and will do whatever I just said earlier. So this can be done. It has been done in various aspects and many years. And now I'm going to go into a system that automatically does these mappings, because up to a few years ago, those mappings were done manually. I remember I was doing those mappings, and actually I had students in my classes. I give them, okay, you create one system, you create another system, then both of you are in one team, get together, create now the top layer. How can I do that? Okay, come up with the mappings. So the mappings at times were manual. Somebody knew what was here, what was there. But the question is, can we automatically generate these mappings? That would be great. That would be great if we can decipher the semantics and extract the semantics from underlying systems. So how to do that? Getting whatever information we can. So this is now, Interplato is a system that we have created to automatically generate mappings between objects in different databases. And initially we have, let's say, 2-3 databases that are, we assume that they can export XML. So we take the XML as a description, and then we can create, let's say, a graph with tables and attributes, just like an ER diagram, something like that, where you have a table and all the attributes around it. The thing is, what attribute map in one system maps to what attribute in another system? And we need to figure that out automatically. So this is work with Leonard Traeger and Andreas Behrendt. And what we did is that we create a graph that represents all this information. And then we start trying to find out the edges. Using a similarity score-based mapping, we can identify edges that are connecting the objects. And later on, we do some post-processing. We create a metadata table, which is the descriptions of the correspondences at the global level. During runtime, if somebody asks a query, then that query goes into this metadata environment, gets all the corresponding information, and automatically generates the subqueries, sends them locally, and then puts back together the information. But the most important thing is how to create the mapping. So we use similarities. There are so many different types of similarity. We use fuzzy search score, and we have two types of objects. For this particular problem, we have tables and we have attributes. So we use fuzzy search score, we use synonyms, we use the data types, if they're similar data types or not. We use the constraint, if they have constraints, if they don't have constraints, what is the type of constraint, is the foreign key or whatever. We have attribute score that now we start putting together the previous results and create new metadata. After we create the attribute score, then we say, okay, if this attribute belongs to this table and another attribute belongs to another table, and we know that those two tables are connected, then the attributes underneath those two tables have more weight. They are more connected. So we use information like that, like meta at the meta level, to generate some kind of another heuristic that we see how those two objects align with each other. And we do the same thing with tables. And then if a table has, let's say, a bunch of attributes and another table has a bunch of attributes, basically we go the other way around. And if those two tables are kind of connected, then if there is some kind of similarity between any of those two attributes, we give them a boost. So this way, we create similarities, but we need to find how to put them together and identify a mapper. So the first thing we do is to more or less do some kind of clustering and see what falls together with each other. And once we do that, then we have, let's say, we sort based on the total number of the similarity score that we used in the previous slide. And then we sort them, and you see here, the results that you see at this point is the potential mappings of customer mail ID at the top level with attributes that are in the local databases. And these are scored and they are sorted. So if we want, we can just take the first one. And we have pretty good chance that this is something that matches. So this is a way to automatically identify kind of similarities using this type of technique. And then using that, you can create the mappings between any kind of objects of the two different databases that you see on the bottom and the global one on the top. So this is a simple technique that actually works. And what we have done is we can just, let's say, all right, experiment a little bit to see actually, do we have success, or when, under what condition it works, and what is the most important thing here. So we have two hyperparameters that we set. One is the ambiguity tolerance. The more ambiguous the mapping, the closer you get more results. And whether we use synonyms or not. You can find a list of synonyms on the web. You can put them together, libraries that give you the synonyms. So if you have synonyms, you have a lot of stuff. For example, clients and customers, right away, they match because they are synonyms. So what is then the output? We evaluated this technique and we found out that if we just do plain similarity, we get, let's say, 55% accuracy. It's not much. We do. Okay, start playing with the hyperparameter. If we put the hyperparameter as 1, that we accept ambiguity, then accuracy goes up to 66, which is still not good. But then if we start doing similarity with synonyms and hyperparameters, we see that the whole thing goes much higher. So you see, this technique actually helps us a lot to identify how to automatically map different objects between databases. So there's a lot of, I just wanted to give you this simple example to provide some very light information about this technique. what we plan to do in the future is that there's already different things like signature of specific mappers or vectorization, like you have embeddings, TF, IDF, word2vec, and things like that. You can also have blocking. Other people have to, put things in blocks that they are pairs that match together. They go into buckets, or filter to discard things that they are not going to match. So what we found out, this is, a lot of people are working with this. We want to do something new, which is called scoping. So what is scoping? Is to sort things and constrain the entity profiles. Like it's a combination between, blocking and filtering, so that you can reduce your space. And I remember one time I was talking with Jai Han. He told me, you have a very big search space. And what I want to do is find an axe. And using this axe, I'm going to chop down the branches that I do not need. Why? Because when you have fewer branches, you reduce your search space. Your algorithm is going to be much faster and you're going to be more efficient. So what's the issue? Find the axe and find the branch. Okay, don't use the axe on the wrong branch. So things like that work. And this is what we plan to use. So basically, if you see there's like related work on vectorization, blocking, filtering, there's nothing on scoping. If you're interested in something like that, let me know. So enough now with systems integration. Let me jump to another application of using semantics in cybersecurity. So cybersecurity, we're talking about intrusion detection techniques and finding cyber attacks. And we all know that there are a lot of IDS system, intrusion detection systems that are out there. And they keep looking into the network and they help identify cyber attacks. What's the problem? Well, take a very conservative approach and they produce a lot of false positives. Things that are not cyber attacks are marked as cyber attacks. Up to the point that cybersecurity analysts do not trust them that much. So we need to improve something there. We need to fine tune and figure out which is a real attack or not. So we want to use some semantic information and provide a more accurate detection of cyber attacks. So now we're talking about semantics and context. As I was telling earlier, you understand a word in a paragraph if you know the context of the paragraph. So the same thing here. We use context and similarities. So context is part of semantics because the context gives you the frame on which you're reasoning about. And in this case, we use, I'm not going to talk about that, but I'm going to go directly into what we use, but more or less, the definition of context is somewhere there. Those 5 things are the different categories of context. And then we can use systems that create a model. And when we create a model, we use it for prediction, filtering, and expansion of cyber attacks. I will talk to you a little bit in more detail about that. So we need to do this into 2 phases. Design time, when we prepare a system, and runtime, when actually we deploy the system out and the system works with whatever network connections we get. So what we want to do? Network connections will go through our system, and the system will decipher those connections and will say, okay, this is a benign connection, let it pass, it's fine. Or this is a suspicious connection. You can either stop it or send it to a honeypot. So we are trying also to do things faster. And we said, okay, forget about packets. I thought I was connected, but I guess we might. Oh. All right. Okay. So we do not want to deal with a lot of information, stuff like that. So we go with a higher level at flows. Okay, we use network flows and try to find cyber attacks using network flows. However, we don't have payload in the flows. What we have statistics, we have some information from the header. How can we do that? Well, we use semantics. So flows are there, and when they pass through, let's say, an IDS system, the IDS system is going to generate alerts. And as I said earlier, these are a lot of alerts. So what we try to do, correlate the alerts with the flows and try to see, okay, what are the alerts that pertain to each flow? Once we have that, then we have information about the flows. What is this information? Information that, let's say, they have start at this time, they end at this time, they contain a lot of, let's say, how many packets, how many octets, flags, protocol, and things like that. But this is good to have all those things, but you cannot really come up with a lot of semantics using those. The most important thing is that you have correlated each flow with alerts from the IDS. And the alerts from the IDS contain a description. So now you have additional information about the description of this particular flow. And what the description gives you is a lot of semantic information. So what we do, some analysis on the description. We get rid of the words, the stop words, and we treat every word as a feature of the flow. So now we have a flow, think of it as an object or a table, as I was saying before, and you have a lot of attributes around it. These are the features. So you can use more or less similar techniques as before at the level of network flows. So what we do, we want to represent all this information in a structure. And this structure is a semantic network. This happens at the beginning when we create a system before we deploy it. So we get a bunch of flows, we correlate them with an IDS, alerts, and then we create a semantic network that contains information about each flow, its properties, and how each flow is connected, or the attacks are connected to each other. So we have attacks as nodes of the flow of the network, and the numbers are how relevant one attack is with another based on the feature of each attack. So we get all this and we put it together and we generate a relevance score, which is basically the sum of all the products of all different paths between any two nodes. So now we have a better understanding of what are the attacks, what are the features, and how each attack is connected with each other. So with this information, we can create a system. This system is on the right-hand side of this slide. And you see that we get, once we have all the semantic network done, we start getting incoming flows. The incoming flows go through a flow classifier, which is basically we have a classifier to give us the first projection of whether something is an attack or not. And if it is an attack, it will tell us where on the decision tree, where on the semantic network is going to land, which is the closest node. So now we have this incoming flow, we pass it through and we see maybe it's an attack and maybe this is the attack that it is. We have landed in one node, in the first node. And then we have a parameter to say, okay, how far out from this node you want to go? Because remember, each node is connected with other nodes that are similar, related. So if you just stay there you're stuck with this answer. But if you say, let me expand my search space a little bit, and you go 2 legs far out, 3 legs, 4 legs, you start collecting additional information from related attacks. So you collect more information, you're expanding your answer. From 1, you have now 2 or 3. So now you have an expanded space that you have as an output. However, this may not be maybe too much. So then what we need to do, we need to cut it down. How do we cut it down? We try to use a filter. What is this filter? It's another classifier that utilizes information about context profiles of each attack. So if some of those profiles are activated and they match some attack from this expanded set of output, that attack is going to be chopped out. So what we do basically, we start with 1, we expand, and then we shrink accordingly. And those 2 expansions and restrictions are leading to better results. So if you look, I'm not going to spend time here, but basically, if you use the semantic network and we use the context information like location, time and location, we get better results than if we do not do that. And we have done this using the data from University of Twente. And we have tried 2 types of similarities, Pearson similarity and Underberg similarity. So these are the results for this, but the most important thing is that try to think outside the box and try to use some smart technique to give you some capability to add more information. Zero-day attacks is another thing that we have done. 0 days is basically unknown attacks. Nobody knows about them, only the hacker who is using them and brings down our systems. So how can we figure out if something is a zero-day attack if we don't even know? Let's see. 0 days are difficult, very difficult. They are being discovered after they have been out for years of use. And then we say, oops, we effed up. So what do? We need to find a way to do it. It is not easy. Also, we need to do something that it is not taking too much time to come up with an answer. So what do? We do not know them. How can we test? So what do? We take a data set that has, let's say, 15 attacks. We remove 5 attacks from this data set. And then we train again our system using the remaining attacks. And during testing, we just give the, all the attacks to the system, including those 5 that were removed, which means that the system had no idea about it, was not trained on them. And more or less, we simulate the environment of a zero-day attack. So what happens? We train those classifiers and we measure the true positives and false positives on identifying 0 days attacks. You see the results. Having a threshold that it is very low, it gives you better results up at the beginning. However, if the threshold is close to 0.9 or 1, it means that you want absolute accuracy and things like that. Very, very, have to be sure. Things go down. So somewhere around 0.5, we have very good true positives and pretty good false positives. So true positives are up, false positives are down. That's what we want. So choosing a threshold around 0.5, 0.6, we are okay. We're doing well. And this is identifying 0 days, which nobody knows about. What's the problem with this approach? It assumes that the 0 days are created based on existing attacks. Is it true? Actually, yes, because hackers can't come up with new attacks from scratch. What they do, they buy something and they try to change the signature and try to change something so that it will not be detected by IDA systems. So most of those fall into this category. So here is a system that not only identifies cyber attacks, but also zero-day attacks to some extent. Okay. So now another area, semantics in anonymization of data sets. It's another problem. I'm not going to spend much time on this. Data anonymization is extremely important because basically we have data sets that contain sensitive information. And this sensitive information is private. Companies generate a lot of data. Take, for example, a hospital with the patients, and they want to analyze this data. They're not capable to analyze the data in-house. So what they're going to do, they want to hire a company, a third party, to do the analysis for them. What's the problem? If they give them the data, they give up all this private information. And they violate privacy laws and all those things. So what happens? They don't give anything. And they do not do the analysis, which is bad. So what we decided to do, okay, let's anonymize your data set in a way that it cannot be re-identified and send it out for analysis. The problem is, will the analysis on the anonymized data set be good enough as if it was done on the original data set? So that's the approach that we use. For example, we started working on this thing, and actually the last bullet there is an interesting one. If you remember, Facebook gave all its data to Cambridge Analytica a few years ago. Cambridge Analytica did whatever they wanted and then started getting money by targeting advertisements to each one of us. And eventually Facebook lost a lot of customers, hundreds of thousands. But anyways, that is the problem. That is the problem. So how can we do that? If we have tried to do that on network data, and you can anonymize a data set. Each column, let's say, you can select whether you want it anonymized or not. So let's take the example of an IP address. So the original IP address is at the beginning on the left. Then what we do a permutation, and then we do some clustering, and then we throw some noise. And this way, it is anonymized. Can somebody with this anonymized data go back to the original one? No, because we use differential privacy, and since there is noise, there's no way to go back. So, okay, we cannot go back. This is good. So this data set can be sent out. Can we use it to have a good analysis on this data set? So we used it again to find out on a data set and try to use intrusion detection techniques, just like I mentioned earlier. So what we did is we did an experiment. On the left, you see the semantic network before anonymization. We did the anonymization. We took the data set and we passed it through the same intrusion detection system. And we got the semantic graph on the right. If you look at those, the difference is very, very minimal. Actually, we measured accuracy on both, and the difference was about 2 to 3% accuracy loss. So when you have things like that, you say, hey, we are on the right track. We can do something here. So now this is a technique that you can anonymize data sets and you can send them out for analysis. And the analysis will be almost as good as if it was done on the original data set. Another one with software vulnerabilities is, I'm not going to spend much time here. You have software, scanners go through the software and they produce a list of bugs. And then the bug list goes to software engineers to fix them. The problem is that there are a lot of false positives there. So how can you reduce the number of false positives? We create a classifier and we go through it, and basically with pretty simple machine learning techniques, we can minimize the number of false positives. The good thing about it is that, and actually the bad thing about it, is that every time you do it, you have to recreate a new classifier for every new software system. You cannot have one and then use it in multiple source code. But the good thing is that you do not need to have, let's say, a training data set of, and use it, have somebody manually label 70% of it. We were able to reduce this up to 10%. With 10% manual labeling, you can find, a regular classifier that does it automatically, and is pretty good. How long does it take for somebody to do 10% versus 70%? Well, 7 times less. So this reflects savings in time and money, and you can do that. But anyways, that's more or less another thing about that. GIS is another issue where you have, in the middle, you see 3 layers, geographic layers, and each one contains different type of information. The bottom one has information about parks in an area. The middle one has information about streets, and the top one has information about zoning, whether something is commercial, residential, or whatever zoning that thing is. And when you have GIS queries that somebody wants to find, let's say, things that are around my street, you want to expand this query and provide additional information, but that information has to be relevant. So what we do, we go up and down in the different layers and link different objects, and we provide the union of those objects that are relevant to the as a result of this query. Okay, so I would like to thank all these people who have basically done all this work. Another thing that I want to bring up here is that the research is good to be published, but it's even better if you bring it to the society or do something about it. Don't just keep it there. So since I like entrepreneurship and all those things, with my students, I said, okay, can we do something beyond that? And we created like small companies, startups. So 3 companies on intrusion, one is on intrusion detection with Ahmed, who was my student at that time. Another one on software security, ML for cyber with Fotini. And another one on anonymization with G1. And is a colleague, and Ahmed, who is now a colleague. So those companies, basically, you try to do something beyond that in order to see how it is when you try to get your idea out and bring it to an environment that it is really brutal. I was really so happy to be present last Saturday at the other one down there in Halepa on the innovation lab, how they call it. Very nice idea. I would encourage all of you to participate in that as much as you can. Get into doing things beyond writing papers. You will see that the world is not only within this environment, but you have a bigger impact when you try to move your work from here out there. So possible collaborations here at the faculty and research level, maybe, we can, if you think that any of those things has anything to do with what you like to do, then please let me know. I learn from you, you learn from me, we get together, do something, and maybe, who knows, have a publication, try to go for funding. At the institution level, there could be some type of changes that we may do. Investigate those things. You never know what may come out of this. So on research collaboration, what I like to go is like this on semantic data science, where in semantics is injected into the various areas of data science, and like in machine learning, in deep learning. And I would like also to investigate linguistic semantics. This is something that will provide a lot of insight and additional information in order to come up with something. So anything like that. I looked around and I saw that the Horizon project has a call for an upcoming deadlines in 2024 on the cluster 5, which is climate, energy, and mobility. If you're interested in those things, maybe we can join forces. So there's something there. Some of them are, I just put 3 of them over there that they may use some kind of semantic information. And between institutions, we may investigate feasibility for exchanging students. You may go to the US, some people from the US may come here, or we can do, let's say, memorandum of understanding across institutions and so on. So that concludes my presentation. Thank you so much for being so patient. And I hope I did not put you to sleep. If you have any questions, please, now is the time. Yes.
Don't forget to ask for the microphone before asking, because otherwise the remote participants.
How do you think that LLMs, large language models, can impact the intuition of semantics?
Excellent question. Excellent question. And actually, when I heard about that first, I said, oops, we have not even looked at that. What's going on here? Everybody is saying, oh, yeah, my homework is solved. Okay, how come a system can? But then I started looking into it and playing with it a little bit. There are some good things about it, and there are some bad things about it. Not bad things, like they do not fit. You have to figure out where LLMs fit. So in NLP, they're very good to synthesize information from here and there. And for example, try to use it with your homework. It depends on the homework. If the homework question is generic, that you can find information on the web, then LLMs are excellent. They will give you the correct thing right away. But if it is something that typically a professor will give you an open question that you cannot really find it out there, LLMs, they have nothing to start with. So LLMs are used, and actually this is part of the linguistic semantics that I talked about there. They have a role, definitely they have a role, but we have to know what that role is and actually what is the boundary of that role. Because they can work well within that boundary, but if you try to get LLMs to work outside of those boundaries, I don't think it works. ChatGPT is an example. How many times it has come up with wrong answers? Now, it is being trained, right? And actually it says, did I do well? All right? Don't answer. Because if you answer, you give information, okay? You're giving a data point. So basically you're expanding their boundary. So they're good, but within this boundary. Yeah. Yes.
Actually, I think there's I'm not sure if it's a side project or it's from Mitre Corporation. If you know them, they are dealing with security. And they're using LLMs to do semantic analysis on unstructured CTI textual data. Until now, they believed in this area of research that LLMs didn't fit. But somehow, I've not looked into it very much, but somehow they managed to do very good semantic analysis using LLMs. and they've also built a framework that does it, and it's open source. So that I just wanted to point it out, that it exists and it can be done. I'm not sure what other NLP techniques or machine learning techniques they use, but it can be done.
Yes, yes. Within the textual area, and the fact that they can synthesize information, that it is found here and there, that helps a lot. The point is, do we have that information to synthesize on? That's the issue. And if we do have, yes, they do well. And this is basically, you are putting things into their boundary so that they can work with that. Definitely. That's why it was in that thing on the future things to do, because things are like that today. Who knows? Tomorrow, it may have a much better approach to this. People are always, they start with something, they take advantage of something else, they put it together and create a better system. So definitely there is future in LLMs. And actually that's I don't know, many people are jumping into it. What I want to say is that don't have too much expectations, but work to make it there. Very good question. Thank you.
Thank you.
We have more people on Zoom. So if any remote participant would like to ask something, please feel free to do so. I think we can hear you. But if there are more questions also in the room, I see faculty members, undergraduate students, postgraduate students, so we have a good audience.
And on a Friday night, Friday afternoon.
Just before the
Yes.
National Day.
Yes.
So one thing I wanted to ask from the very first part of the talk, where you have two, let's say, databases with different attributes, different tables, and automatically you find some similarities. I can see how you can identify the similar attributes and tables when you have databases that have the same kind of data. Let's say a company that rents cars, another company that books hotels, and then a third with flights or something. But if for some reason I mix two databases that are completely irrelevant, let's say, one to each other, what will happen with those automatic methods? I was wondering, what the outcome will look like.
Yeah. Very good question. Yes. And actually, this is something that we tried and we saw the results and we started working on it. So what's happening is that you get something completely out of the blue. It does not really do anything. It basically gives you, let's say, a blank, or the scores are more or less the same. And then you do not know what to do because the system could not really find correspondences since the correspondences do not exist. So what we try now, we have, let's say, 4 databases that are more or less on similar things, and a 5th one that is completely out of the blue. And we try to figure out, can we identify cases like that? Because this is also extremely important to know whether things match and also when things do not match. So we use now some new techniques. We have not found the answer yet. We're thinking of, trying autoencoders and figure out whether something is going to come up with in combination with clustering. So that is giving us something, but I do not want to say yet because we're not sure yet. But actually this is something that we currently are trying to solve. It is an important problem. We need to know how to figure that out. Yeah. Hopefully soon.
That will be the subject of the next talk, I guess, right? Thank you. So, any more questions or comments now that we have our speaker here?
Well, I'll be around until end of November, so anytime drop by, I don't know where I am, like one floor below.
Yeah.
Okay, the label says Kosmitoras, but I am not. Okay.
It's the so-called office of the dean.
Office of the Dean. Okay. Yeah. So
It's usually
okay.
used by visitors. So if there are no more questions, then let's thank the speaker once again. Thank you.
Thank you.